in space, there are millions of unknown worlds, sailing on vast journeys across the solar system and beyond, sometimes appearing as spectacular visitors in our skies. Comets and asteroids. These small, irregular-shaped bodies are helping us to understand profound questions about the Earth, the solar system, and even life, as well as provoking new questions. The Sky at Night has covered every major space science discovery in more than 60 years of occasionally quirky broadcasting.
It's absolutely tremendous!
I'm going to do just a little mathematics. Please don't be frightened.
And now, we're going to use that archive to take you to the edge of the solar system and beyond.
Good evening.
Welcome. Good evening.
Welcome to the Sky at Night Guide to Comets and Asteroids. We tend to think of our solar system as one star with 8 planets in orbit about it, but there's so much more. Comets, asteroids, and other small bodies, anything too small to be classed as a planet, are strewn across our cosmic neighborhood and way out into space. Their small size and great speed has, until recently, made them hard to study. But now, these varied and mysterious objects have become an exciting new frontier in space exploration. There are many questions to answer. What are they made of? Where do they come from? And what can they tell us about the history of the solar system and the Earth? Comets are the most visible of these objects, and one of the great wonders of the night sky. For centuries, they have captivated us. In fact, a newly discovered comet was the subject of the very first episode of The Sky at Night. Unfortunately, that episode no longer survives, but we do have a programme from 1967 looking back to the first transmission.
At the end of April 1957, we came on with the first Sky at Night program, and we were heralded in by the Aderin-Pocock comet, which was the brightest comet that had been visible with the naked eye from Britain for a great many years. And this is the very first caption we showed on the Sky at Night. I did wonder, at that time, whether the comet would prove to be a good omen or a bad one, but at any rate, the Sky at Night is still running.
Comets can sometimes be spotted with binoculars, and even with the naked eye. Their most famous and distinguishing feature is their long tail, stretching out across the night sky. One of the first great questions about comets were all about those spectacular tails. Now I have here in front of me one of the original copies of Sir Isaac Newton's Principia. It caused a real revolution when it was first published in 1687. And inside it details his theories about gravitation and the solar system. On this page, we see Newton charting the path of the great comet of 1680. Now, the interesting thing is, the comet's tail always points away from the sun. Now, Newton didn't know what the comet or the tail were made of, but he thought that the tail had to be in some way linked to the sun. He was right. We now know it's the sun's energy that generates a comet's tail. Solar wind and radiation pushes particles of dust and ionized gas out from the comet, millions of miles into space. Seen up close, there are often actually two tails. The heavier dust particles fall in a curved tail, Meanwhile, the much lighter gas particles are blasted in a straight line away from the sun. Fueled by the blazing sun, these tails can be the most jaw-dropping objects in the night sky and can be seen from all over the globe.
Talking about comets, we may be in for a really good one.
But they don't always match our expectations.
In 1973 came Kohoutek's comet. It was billed as the comet of the century.
Comet Kohoutek is on its way. Visible between mid-November and late January, it will eventually be as bright or brighter than the famous Halley's Comet of 1910. 4 NASA spacecraft, sounding rockets, balloons, Skylab, ground-based observatories, and telescope-carrying aircraft like this will team up to form the most comprehensive comet watch ever planned.
After the last observations from Seki, we can expect the maximum brightness of this comet to be of about -4 to -5.
That's about the brightness of Venus, in fact.
Yes.
And so this is going to be a really spectacular comet, and it's not going to disappoint us. It's going to be remembered for a very long time.
It will certainly be remembered, but not in the way we expected. It was widely regarded as the non-event of the century.
But under the right conditions and with the right equipment, even the faintest comet can be quite a spectacle. 40 years after the Kohoutek debacle, the Sky at Night team travelled to La Palma, one of the best astronomy sites on the planet, for the arrival of Comet Ison.
It's 6 a.m. and we have an incredibly short window to find the comet.
So Comet Ison has just risen above the horizon. I've managed to get it in these binoculars. It's a faint blob with a tail just streaking upwards away from the horizon, away from the sun. But what I really want to do is try and get it in one of these telescopes to get a really close-up view of it.
Pete, how have you been getting on?
Fantastic. I mean, it's a fantastic comet to take a photograph of, and I'm picking up quite a bit of the tail as well. Do you want to see a picture?
I do.
Okay, be prepared then.
Okay, you're going to wow me.
Look at that.
You are wowing me. Fantastic. So you can see the head there.
If I zoom in a bit, you can see some of the structure.
I wasn't expecting to see that level of structure, but I can see 1, 2, 3 very clear bands in that dust tail.
Yeah.
Really nice.
And the head has got a definite greenish tint to it, hasn't it? Isn't that gorgeous?
Of course, comets always cause great excitement.
Comets are so obvious and spectacular. We've been observing them and commenting on them for millennia. They were seen as omens and have often played a vital role in ancient history.
And it was, in fact, seen in 1066, just before the Battle of Hastings, and it's recorded there on the Bayeux Tapestry. That appears to have struck alarm into the hearts of the Saxons.
It wasn't just in the Western world that comets loomed large in history. In 2015, the Sky at Night investigated the role of comets in ancient China.
So, Christopher, tell us what we're looking at here.
We're looking at a chapter of the Hanshu, a history of China written in about 100 AD. And this is a record of phenomena seen in the sky.
And how accurate a record is this?
This was written by professionals. The Emperor maintains a staff of sky watchers whose job is to be up there noting down everything that happens. And there's a reason for that. It's explained on the first page of this chapter. Stars and planets, all the lights up there are a great control panel of indicator lights. If a light appears where it's unexpected, that means something big is happening, because everything in the sky mirrors what's happening on the Earth.
So it was portents and omens of what was going on in the sky reflected human concerns.
Yes.
Is there anything of note in this book that we should look at in terms of bright objects?
And we come to near the end of the chapter and we see a broom star appeared in the constellation of the Ox for more than 70 days. So the fact it was up there for so long means that it really shows something big.
This broom star, this comet, would have been seen in the Middle East as well.
Absolutely.
Wow, that is really interesting.
Around the same time, about 2,000 years ago. There's a similar description in ancient Babylonian tablets from the Middle East.
And it tells us that the comet appeared for the first time in the northern part of the sky in the area of Taurus and the Pleiades.
This has even led to speculation that a comet could have been the inspiration behind the Star of Bethlehem. As we discovered more about comets, one of the big questions concerned where they came from. Why did they appear seemingly at random in the sky? Over the years, astronomers started to notice patterns in their appearances. This is a picture of a comet, originally seen in 1531, and this book was published just a few years later. You can see the tail of the comet streaming away from the body, but also streaming away from the sun. 151 years later, Edmund Halley saw a comet following a very similar trajectory.
Halley calculated the orbit, or path, and he found out it was remarkably similar to orbits of comets previously seen in 1607 and 1531. And he made the very bold prediction that they were one and the same comet that came back once every 76 years. And therefore he forecast they would be seen again in 1758. He was, of course, absolutely right.
Halley worked out that comets orbit the sun, just as planets do, but on highly elliptical paths that bring them close to the sun and the Earth for a short time, before shooting back out into space. But that still left open the question of where exactly do comets come from? It's a question that is still debated today. We think that Halley's comet, and others like it, originated into the inner solar system, are thrown out of the Oort cloud by chance. The passing of a neighbouring star, or a chance collision, ejects them from their distant home and sends them careering in towards the sun. After a comet leaves the inner solar system, they might not be seen for hundreds or even thousands of years, but they do leave something behind in their wake. And this is a source for another wonder of the night skies.
As comets move, they leave debris behind them. Obviously, we can't see it because it's much too small and much too faint.
But when the Earth passes through this debris stream, something amazing happens. The particles of dust become something else entirely. Meteors or shooting stars.
If a meteor comes close to the Earth, below something like 120 miles, it enters the upper atmosphere, and then it has to push its way through the air. That sets up friction, that in turn causes heat, and the meteor burns away in the streak of radiation that we call a shooting star. And that is all a shooting star is, a tiny particle dying in the Earth's upper atmosphere.
Oh, that was a nice one. Well, Perseus has risen, it's dark, I've already seen my first meteors of the evening, so we're using an infrared camera to avoid disturbing the observers.
In 2007, the sky at night went meteor watching.
So Bruce, how's it going? Have you seen many meteors?
Well, it's early yet, Chris. Just getting set up, getting ready for the show.
There was one, a small one anyway.
There was one, a faint one, you see it?
No, I didn't. I was looking down at that moment.
That was a Perseus, all right. I haven't seen any really bright meteors, and certainly nothing in the nature of a fireball.
I've seen one or two of the smaller meteors, and a couple which I think are almost what's termed the fireballs.
Yes, the really spectacular ones.
That leave a trail. A couple of those.
Those fireballs, if you do see one, it can stay with you for years, can't it? You don't quite forget them.
I've never watched the skies in the company of so many people, and that makes it far more fun.
Although, like you say, every time I hear a cry go up, I think that's another one I've missed.
Yeah.
And having the radio in the background's quite fun, isn't it?
Oh, yes. As soon as you hear it go bong, you want to see what it is.
Yes.
Watching meteor showers like this is a beautiful way to see the remains of now distant comets. It's amazing to think that these particles could have even come from comets like Halley, that are now in the far reaches of the outer solar system. billions of kilometres away.
Oh,
meteor.
See, my finger was not on the button, but we did see that one. But if I point my camera at an area of the sky, it's guaranteed there will be no meteors. That might be a useful thing to...
Yes, you should investigate that. There's some new physics there somewhere.
Yes, yes.
Excellent.
So far, our focus has been on comets. But there's another class of small object moving around the solar system, but they're much harder to spot. Rather surprisingly, it might be better, rather than looking up into the night sky, to look down instead.
I'm walking along the rim of one of the most remarkable places in the entire world. This is Meteor Crater in Arizona, a huge gaping hole in the ground over 4,000 feet across. Just look at it. Down there, the floor is nearly 600 feet below me. There's nothing else quite like it anywhere in the world. It was made by a meteorite, a huge chunk of material, mainly iron, weighing probably a couple of 100 tons, that came from space and blasted out, leaving this hole in the desert that you can now see. Quite a lot of rough ground here. It's rather steep, as you can see. Yes, quite so. It's rather crumbly, too. But it's not awfully difficult to maneuver once you get the hang of it. Remember, this was created by a vast explosion. It wasn't a gentle process at all, an absolute inferno when the meteorite first struck. Just look at this rock, for example. Well, I don't know how much this weighs, a very considerable amount, and it's just been hurled up here by the force of the explosion.
Most craters are destroyed by the Earth's constantly changing surface. But from space, it's possible to see a few of these scars that have survived. The Manicouagan crater in Canada, at 70 kilometres wide, is one of the most impressive. It was formed by an impact over 200 million years ago. The Tanuma crater, deep in the Sahara Desert, is another rare example of one that has survived. This is part of an asteroid. When objects like this land here on Earth, they're called meteorites. Lumps of rock and metal that have survived passage through the Earth's atmosphere and sometimes land with explosive impact. This one landed in prehistoric times, and parts of it have been found all over Namibia. When a large meteorite crashes into the Earth, both the meteorite and the Earth's surface undergo some of the most violent transformations we know of. In 2014, the Sky at Night investigated the physics behind meteorite impacts.
I've come to Cranfield University, where the Dynamic Response Group can recreate meteorite impacts in miniature and reveal the key transformations that occur. To see it, we're going to fire an object faster than the speed of sound at a solid target.
I've got a lead ball and we're going to shoot it using this high-pressure gas gun. High-pressure helium is going to shoot it down the barrel. It's going to reach speeds of up to 350 meters per second. It's then going to hit the target. It's going to come to a dead stop. And that whole process is going to take about a hundredth of a second.
OK, Dave, tell me when.
Just about.
And as that energy is released, it's going to make solid metal act in an extraordinary way.
Let's go. OK, ready, firing. Clear.
Clear.
OK.
We can see the gas damage. Oh yeah, very nice crater produced by that impact. Have a look at that. And what you're seeing is this material behaving not like you would expect a solid to behave, but actually more like a fluid.
Now, all that happened pretty quickly, and even when we slow the footage down 800 times, the moment of impact lasts just a second. The kinetic energy of the projectile, travelling at faster than the speed of sound, has to be absorbed into the target as it comes to a sudden stop, and it's that shock wave of energy that causes the material to flow. This liquid-like behaviour is key to understanding what happens during meteorite impacts, and it also provides another way to study them.
So one of the simplest ways of looking at this and exploring the mechanics of asteroid impact
is to look at the impacts of fluids. And there's an easy way to do that, which is just to get a pipette and a bowl of water and impact one fluid, i.e. a drop of water, into another, which is the bowl of water. The fact that in the moment of impact, solids act like fluids means that you can use something as simple as a water droplet to reveal the processes at work when a meteorite hits the Earth. So here comes the droplet, and as it impacts the surface, you can see that immediately it starts to flow. Now, of course it does, it's a droplet, but this also happens in rock and in metal, as we saw earlier. But still, you can just see the hemispherical droplet, so half of the droplet in a way, doesn't know that the front end has hit. It's still going. The momentum's carrying it forward, and off it goes, making the crater deeper and deeper and deeper. The result is that the back of the droplet drives on through the middle, pushing the surface out and up. Meanwhile, the shock wave is making it wider and wider as it comes out. And on the process goes until you get this classic crater shape.
Asteroids are quite different from comets because they are mainly rocky or metallic and, crucially, don't contain the ices that form a tail. Their composition isn't the only thing that distinguishes comets from asteroids. Their origins are also different. Most asteroids originate in a very particular area of the solar system.
So, first of all, where do we find most of them? Our solar system is divided essentially into two parts. We have 4 fairly small solid planets: Mercury, Venus, the Earth and Mars. And then beyond the path of Mars, we have a wide gap before we come to Jupiter, which is the first of the giant planets. And it's in that wide gap between the paths or orbits of Mars and Jupiter that we find most of the asteroids or minor planets.
With the exception of 1 or 2, most asteroids are too small and too distant to be seen with the naked eye. So it wasn't until we started to use photographic plates to image the night sky that asteroids started to show up as strange streaks in places they weren't expected.
Not all astronomers are very happy about the asteroids because they do leave their trails everywhere, sometimes on plates exposed for quite different reasons.
Within the asteroid belt between Mars and Jupiter, there are thought to be around 1 to 2 million of these small objects, ranging in size from a pebble to almost 1,000 kilometers in diameter. Unlike comets, asteroids formed in the warmer regions of the solar system, much closer to the sun, so they are less icy and more solid and self-contained, more like miniature planets.
And to show you what the sizes of the asteroids are, let's compare them with the size of the British Isles. We've got a map there. And let's begin with Ceres, number 1 of the group. As I say, discovered in 1801, over 600 miles across, and that, as you can see, is quite sizable. The second asteroid to come to light was number 2, also the second largest. That is Pallas, rather smaller than Ceres. Put Pallas in there. And then, a couple of years later, along came asteroid number 3, which is now known as Juno. Juno is actually not one of the largest of the asteroids, but it was number 3 to be discovered, so it has a special place. And the size of Juno, well, there it is, around Juno. And then along came number 4 in 1808. That is Vesta, very nearly as big as Pallas, and actually the brightest member of the entire asteroid swarm.
But what's really interesting is that we've been able to study asteroids by collecting their fragments that have crashed into the Earth as meteorites. You can see that this meteorite is quite metallic. In larger asteroids, iron-rich material melts and sinks to the core, just like with planets. So this meteorite comes from the core of a large asteroid or a planetesimal. We believe that this meteorite came from the asteroid Vesta, but it looks quite different from the first. If you look at Vesta through a telescope, you can see that the surface is peppered with craters. This is where other asteroids and meteors have crashed into the surface, throwing up ejecta that has landed here on Earth. So this is meteorite that is evidence of a violent past. All these meteorites are relatively young compared with these, which are much, much older. This is a section taken through one of those meteorites, and you can see these grains. They're called chondrules, and they're one of the oldest things in the solar system. They're formed from molten material, but exactly how they formed is a bit of a mystery. There is one asteroid that stands out from all the rest, because it changed the course of history here on Earth. Around 65 million years ago, an impact in the asteroid belt knocked out an object 10 kilometers wide and set it on a collision course with our planet. The impact led to the extinction of 3/4 of all the species alive at the time, including the dinosaurs. It struck here in modern-day Mexico. The impact was so long ago that the evidence for it has since been hidden by the Earth's changing surface. But we can see clues of what happened in rocks found around the world.
It's one of the most remarkable things I've ever seen. This line here marks the point, the exact moment at which the asteroid that did for the dinosaurs hit the Earth. And up here above it is clay infused with iridium. That iridium is the fallout from the meteorite. It came from space. But what's really remarkable is that this rock doesn't come from Mexico, where the impact occurred, but from Copenhagen, more than 5,000 miles away, showing that the asteroid changed the future of the entire world.
But we don't just see evidence for meteorite impacts here on Earth. Back in the 1960s, with data streaming in from spacecraft, we began to investigate craters on other worlds, planets and moons throughout the solar system. At the time, there was considerable debate as to what caused these craters. Impacts was just one theory.
I've made a model of a typical lunar crater, and as the sun slowly rises, you get the central peak, the shadows inside draw back, until finally, when the sun is high over the crater, there's no shadow left inside it at all. In fact, some of these lunar craters turn out to be very deep indeed, and the deepest of the lot is called Newton, and that has walls which are 30,000 feet above the bottom of the floor. So if you put Mount Everest inside it, not even the top would poke out.
At the time, many scientists thought that these must be volcanic in origin. It seems strange that we saw so many on other worlds and so few on Earth.
Now, we don't quite know how these craters were formed. Personally, I think that the large ones are probably volcanic, although some people think that they're due to meteorites hitting the surface. Well, that remains to be cleared up.
Now, there are two schools of thought. Either the craters on the moon were made by volcanic action, or else by meteoritic impact. And I think most people nowadays, including myself, agree that you must have craters of both kinds.
It's now widely accepted that most of the craters we see around the solar system were in fact formed by impacts with other bodies, not volcanoes. We see them everywhere, from planets to moons, and even on the surface of other asteroids. In fact, the places where we don't see craters are almost more intriguing. Worlds like Pluto, Jupiter's moon, Europa, and of course the Earth, have fewer craters than other worlds of the same size. This tells us that the surfaces are young, geologically speaking, that some kind of active geology is taking place. Our understanding of asteroids has been transformed by studying what happens when their fragments hit planetary bodies. But to increase our knowledge of asteroids and comets, we need to see them in their original state. But to encounter them out there in space, up close and personal, is easier said than done. The easiest way to study an asteroid or comet in space is to wait for them to come close enough to Earth that we can see them.
Way back in 1937, I remember reading a rather interesting headline in the London Times, and there it is. Earth escaped from collision. Minor planet missed by 5.5 hours. And that was indicative of the pass of a very small body, about a mile across, an asteroid or minor planet, we now call it Hermes, which grazed us at a distance of something like 485,000 miles, which is less than twice the distance of the Moon.
In 2013, we had an even closer call.
In just a few hours' time, an asteroid will be making one of the closest approaches to Earth in recent years, and we're hoping to see it.
The team came to Kielder Observatory in Northumberland in the hopes of catching a glimpse of this rocky visitor. Though small by asteroid standards, it passed so close to us, beneath the orbit of our communication satellites at just 28,000 kilometres, that we stood a chance of picking it up with telescopes.
It's completely dark now, and the night skies of Kielder have really delivered. We're out on the observation deck, waiting to see the asteroid come into view. The reason we're here now is that it's about to rise, as seen from here in Kielder, and we should see it go up, I think, just beneath the tail of Leo there, and then by 9:30 it should be up crossing the plough, and it will be visible in telescopes but also in binoculars, so I'm looking forward to having a look at it.
I'm wondering what it's actually going to look like, this Olympic-sized swimming pool, that sized object travelling at 5 miles per second.
It should be rising, so should we go and have a look?
I think we should, yes, I think we should. Let's check it's on the course they said it was. Yes.
I'm hoping that the skies stay clear enough that I can get a view, even though it's going to be rather faint.
Yes.
Asteroid 2012 DA14 is now in our sky, but it's proving very, very difficult to see.
That's right, yeah.
Is that as it gets to that point, which is easy to locate, it will have got dimmer.
Yeah. Does somebody have it?
I've got it.
You've got it?
Yeah, I can see the thing moving.
Yes.
Yeah.
Where?
Well, right at this moment, the asteroid is with us. Pete Lawrence there with a great sense of determination. He is on it. He's got his camera going. He's collecting lots and lots of pictures of it. You can actually physically see the asteroid moving.
Got it.
Ah, and Paul Abel has it now. What can you see, Paul?
Well, it's a tiny faint point of light, but it's moving noticeably against the background stars. I'm quite surprised that the motion is as detectable as this. You seen the motion, Pete? It is quite remarkable.
It's absolutely incredible. I've never seen anything like it.
Me neither.
It just looks like a faint star, but you can see it visibly moving through the binoculars. I expected to see something that would look stationary, and then you'd come back to it a moment later and you'd see it would have moved, but I can actually visibly see it moving. That's just astonishing to think that is an asteroid about 45 metres across, moving through space. I'm very glad I've seen it here from Kielder as well.
This footage was made by NASA's radar observations as the asteroid passed the Earth. It tumbled past us and out into deep space, never to be seen again. Asteroids may have one other wonder to offer us in the night sky, and with it, a chance to get an even closer look at their composition.
The light evenings of the summer months aren't always great for stargazing, but they do mean we have a chance to see a stunning byproduct of asteroids. About an hour after sunset, you might see, towards the northern half of the sky, wisps of golden, white or electric blue clouds that are obviously bright against the darkening sky. These are called noctilucent clouds. These clouds are essentially a thin veil of water ice up in the highest reaches of our atmosphere, up in the mesosphere as it's called. Now, they're about 50 miles up, which is about 7 times the height of the highest normal clouds. And here, they're right on the edge of space. All clouds need something, such as a speck of dust, for the water droplets or ice crystals to form around. But it's really difficult to waft dust particles right up into the mesosphere. Now, some scientists believe that the particles which populate that really thin layer in the mesosphere in which noctilucent clouds form may have come from comets and asteroids.
These dust particles are within the range of high-altitude aircraft, so we can bring back samples to analyse. This is what they look like up close, under a microscope. Fragments of comets or asteroids lingering in our upper atmosphere. The trouble is, we can't pinpoint the source of these particles or know how long they've been there. What scientists really wanted was to sample a comet or asteroid out there in space, undisturbed and complete. In 1985, the European Space Agency launched a probe towards a target that has mesmerized humankind for millennia, Halley's Comet. And of course, Sky at Night didn't turn down the opportunity to tag along for the ride. No one had ever seen a comet up close. Comet tails were relatively easy to study. They're big, bright, and easy to see. But what lay beneath, inside the tail, was more of a mystery. Over the years, scientists came up with a theory. Underneath the tail was a ball of rock and ice, probably only a few kilometers in diameter. This hidden central core was really the essence of the comet.
We know something about the anatomy, and we know that a large comet has a central nucleus, and that's really the most mysterious part of the comet. It's probably made up chiefly of ice, and it may be a mile or two across. We don't really know. When the ices are warmed, they start to evaporate, and the nucleus hides itself inside the head or coma, which is why we've never yet seen a cometary nucleus.
But everything up until this point was conjecture. There was only one way to confirm this theory: to go there and see for ourselves.
July the 1st, launch day -1, halfway through the long countdown procedure. Ariane is ready to go.
Scientific and television history in the making, as Patrick Moore sets the scene for tonight's celestial encounter.
Good evening, and welcome to our Night of the Comet. Within the next hour or two, we may learn more about Halley's Comet, our most famous cosmic visitor, than we've done since the start of human history. The European Space Agency is sending its first deep space probe, Giotto, right into the heart of the comet. Something that's never been done before.
4, 3, 2, 1, top!
Ignition. Ariane first stage ignition and takeoff.
The object of tonight's mission is to follow Giotto all the way in. At the present moment, it's something like 250,000 kilometers away from the nucleus of the comet. At closest approach, in just over an hour's time, it'll only be 540 kilometers away. And it's then, if at all, that we're going to see the nucleus. We've simply got to wait and see. Here's the science area. And of course, there's the control room, which recently had the job of directing the spacecraft for its precise distance from the nucleus. This is where the information from the comet is being received, but the real action is taking place over 90 million miles away.
We have preconceived ideas about the nature of comets. We believe that there's a comet nucleus in the center. We have some ideas about the origin of comets. We have pretty good ideas how much dust and gas to expect, but I'm sure there will be major surprises.
So is the nucleus really a dirty snowball? That was the theory put forward by Dr. Fred Whipple over 30 years ago. What evidence are you looking for from Giotto?
Well, particularly the shape and the surface characteristics of the nucleus, because so far this has been entirely a matter of imagination. Now we will see the real thing.
Hello, this is James in London.
Getting some very interesting
Can I interrupt, because I hear that we're getting live pictures in from the dust detecting equipment, and you can see...
Then we actually lose the signal.
Despite the loss of signal, Giotto still successfully managed to pass the nucleus with a distance of just under 600 kilometers. One impact had knocked the spacecraft off axis, so its antenna no longer pointed towards Earth. Another impact had smashed the colour camera, but not before it had managed to photograph the nucleus at closest approach. After some processing and analysis, this is what the images revealed. Much as expected, a rocky, icy nucleus, spewing out gas and dust into space. Comets underneath the tail appear to be rocky worlds.
Using the pictures as a base, astronomers have made a model of the comet's nucleus. It looks a bit like a battered peanut, but you can clearly see the rifts, valleys, and craters. And of course, it's a measure of the camera's achievement that enough details were shown to make this model possible.
Giotto had been an amazing achievement. but it only got a fleeting look at the comet, and it had captured it with instrumentation that by today's standards was primitive. And key questions remained unanswered.
We believe that the solar system began somewhere between 4.5 and 5,000 million years ago as a cloud of dust and gas surrounding the youthful sun. We call that the solar nebula. And gradually, that gas started to condense out into blobs or planetesimals. And from that, the planets actually built up.
Scientists believed that comets were the leftovers from the beginning of the solar system. Pieces of rock and ice that never got turned into planets. So seeing one up close and for an extended period would allow them to study the stuff from which all planets and ultimately all of us were formed. In 2004, the Rosetta mission was launched. Its objective was to track down, catch, and eventually land a small probe on a comet less than 5 kilometers wide and traveling at 50,000 kilometers an hour.
Rosetta is one of the most exciting and ambitious missions ever attempted, like something straight out of science fiction. There's a 6 billion kilometre journey, a rendezvous with a comet, and then, if all goes well, a landing on the surface using harpoons and grappling hooks. It's a wonderful scientific mission, but it's also a remarkable feat of engineering.
The aim was to answer big questions about the early history of the solar system and about our own planet. But first, they had to get the Philae lander from the orbiting Rosetta spacecraft down to the surface of the comet.
Behind me is the heart of it all, mission control. In there are some people that have had a rather sleepless night keeping an eye on things, and there's some news. The bad news is that one of the critical systems on the Philae lander, the thruster that would have pushed it into the surface of the comet and kept it stable, seems to be malfunctioning. But the team have decided to go for a landing anyway, and the good news is that Rosetta is perfectly on course to make that happen.
Now, there it looks quite calm at the moment, but it's hotting up because in the next few hours they're going to be releasing the lander. And when that happens, I think all hell's going to break loose. Philae separated from Rosetta and plummeted towards the comet at walking pace, taking 7 hours from release to touchdown. It was a journey fraught with risks. And the closer it got to the surface, the greater the danger. The lander needed to avoid an array of obstacles, like cliff edges or boulders, that could cause Philae to flip over on landing. A mission 25 years in the planning all came down to this moment. The atmosphere in the room was incredible as we waited for the crucial signal, to hear Philae speak to us from the surface of a distant comet.
Well, it's pretty tense in here now. The quiet excitement of earlier is gone, and there's a lot of nervous people. We think the landing may already have happened. The signal could arrive any minute, and all we can do here at Mission Control is sit, wait nervously, and watch for that signal.
It seems quite likely that the Philae has already landed. It's on the comet, but of course it's 500 million kilometers away. Finally, after 7 hours of slow descent, the time for the landing arrived, and then passed.
The room's gone a bit quiet, but nothing yet, and the team in Mission Control look pretty static, so we're still waiting.
And the world is watching. I'd hate to be in there.
They'll be running through their checks. They'll have a long list of things they need to check before they tell us anything. We've got 2 days, so the lander will probably live now for months, but it's got a battery for 2 days, and all of its individual instruments will scratch and sniff and taste the comet. We've never done this before.
The early optimism didn't last. The Philae lander stopped communicating with Earth a few days after touchdown. It turned out that Philae had bounced across the surface after its landing harpoons failed to deploy, ending up under a cliff with no light falling on its solar panels and therefore no battery power. Although the lander was lost, the orbiter continued on with its mission for another 2 years. Its main goal was to help us find out how the planets were formed. Clues would be uncovered when Rosetta sent back its closest images of the surface yet, revealing mysterious pits.
The exciting thing is that if you look particularly over to the left-hand side of the pits, you can see this nodular structure. You've got these little
balls,
these little balls. They're about 2 or 3 meters across, so pretty
So not
large.
that little. That's sort of this sort of size.
Absolutely, you do have difficulty putting your arms around them. But the important thing is that Rosetta sees these wherever it sees exposed surfaces looking into the inside and interior of the comet, which implies that these are fundamental building blocks of the comet. And it could be that we're seeing signs here of the first objects that formed in our solar system.
So the natural size for these things is a few meters across.
Absolutely. Now there's some work going on that implies that these 2 or 3 meter boulders themselves are composed themselves of smaller pebble-sized objects. And so we could be getting our first measurements of the real way that Mother Nature makes boulders, then comets, larger objects, and finally planets like the Earth.
Comets have given us a window to the very beginnings of the solar system. But scientists now wonder if they can also answer one of the great mysteries of our own planet.
Now, we know that all the material in the universe is made up of 92 fundamental elements. Now, I've got examples of some of those elements here. Here, for example, is tin. Here is some lead. Here is carbon, silicon, and a gas, helium, and a liquid element, mercury. And we can show that all the material in the universe is made up of combinations of these 92 fundamental elements. This is not speculation, this is fact. Now, we also know that there are only 2 elements whose atoms are physically able to build up into the large and complex atom groups or molecules which we need for living life. Those are carbon and silicon. And silicon's not very good at it, and so I think we must resign ourselves to the fact that living creatures, wherever they may be, must be based upon carbon.
The 2 main requirements for life are water, a solvent for dissolving and transporting nutrients, and carbon, an element capable of bonding with many other elements and building up complex molecules. Scientists have long wondered whether these life-sustaining molecules, known as organic compounds, were present on the early Earth. The question was, where did these organic chemicals come from, and how early did they appear in the solar system? Well, once again, Rosetta provided the answers, and the key was to analyse the comet's emissions with forensic detail. When it first arrived in orbit around the comet in August 2014, it was 500 million miles from the Sun, and the comet's nucleus was largely frozen and dormant. But as its orbit brought it closer to the Sun, we could see it burst into life. These 3 images show a period of just 36 minutes on the 29th of July 2015. In this middle image, we see a vast but short-lived jet bursting from the surface. It's caused by ice below the surface, converting into gas and then shooting out into space. Other outbursts have been even more dramatic. On February the 19th this year, a huge event, thought to have been a landslide, caused a massive cloud of dust to erupt from the comet, resulting in a 6-fold increase in brightness. It's this sort of sudden and rare event that would have been almost impossible to observe if we had not been studying the comet for a long period of time. As the comet neared the Sun, its ices warmed and more dust was ejected. And within that dust, Rosetta's instruments detected something quite extraordinary. Organic chemicals. Amongst them, amino acids. The very building blocks of life. They are what DNA and cell membranes are made of. They are part of every living thing on our planet. Whether or not these compounds were delivered to the early Earth by comets is still a mystery. But we know for certain that these potential seeds for life must have been sown far and wide throughout the solar system's 4.5 billion year history. Over the years, our exploration of comets has revealed some spectacular results. And astronomy on its head. The discovery of the first interstellar object.
The brightness of the object was changing over time.
Yes.
It fades quite dramatically
It
and then
changes
recovers.
in brightness over a remarkable amount of contrast, and we weren't expecting that. That was great.
What do we think causes that variation?
Probably the shape of the object. Here I have a sun.
Okay.
Here I have a turntable that is rotating an object over time.
Okay.
So the camera is watching this object. Let's try this with something a bit stranger in shape.
Okay, I'll remove the sphere. There we go.
Instead put on this delightful potato asteroid here. What the camera is seeing as this point of light changes in brightness as it turns is when the short end is pointing towards the camera.
Like it is now.
You have minimum surface area being reflected the light, so it's dimmest. And when it turns round and the whole side of this object is being illuminated, it's the brightest to the camera, and so you see this brightness peak.
And what do you find? What shape is Oumuamua?
It's actually got to be even more elongated than this little potato. This is 3 to 1. Oumuamua has to be at least 5 to 1.
This is an artist's impression of what Michelle and her team observed. A cigar-shaped asteroid tumbling through space.
It seems to me very unlikely that the first interstellar visitor would be this unusual. Is that something that disturbs you, or does this make sense if you've been thinking about these things?
The shape is a bit unusual, but that the colour is so much like what we see in our own solar system, there's a kinship there. It tells you that something that formed around a different star and something that formed around our own star have a lot of similarity in their surface.
And so, our first interstellar visitor left our solar system as it entered, tumbling silently into the darkness. And what a profound moment in history this was, to be able to see and study something that had come from another part of the galaxy, to be able to study and understand something that had been born and lived around another star. But what I found truly amazing is how similar this object was to the comets and asteroids that we find within our own local solar system.
The physics and chemistry throughout all the millions of galaxies is much the same.
Bricks of the universe are the same everywhere.
Yes.
Maybe we're not as unique as we once thought. Through over 60 years of the sky at night, comets and asteroids have been with us all the way. They've taken us back to the beginning of our own planet's history. They've been the scene for some of our greatest feats of space exploration. And they continue to surprise us.
And I just wonder, how many people remember this picture, the very first one we ever showed in April 1957? And this was me in the same year. Times change. Well, I'm afraid we're not going to see that comet again. It's been thrown out of the solar system and is now wandering thousands of millions of miles away between the stars. And I shall always remember it with very great affection.
Unlike planets and moons, we only get a fleeting glimpse of comets and asteroids. And it's this rarity, this mystique, that makes them such special visitors. Who knows what the next one will reveal?
Your Christmas sorted with the best of 2019 on BBC iPlayer, including Brian Cox and the Planets, streaming now. Here next, one man devoted to saving a feared and hated animal. Meet the Batman of Mexico.